And so we'll start with the radiographic imaging. We're going to talk about the physics, some information about the technology itself, and then the devices. And each one of them will go and cover the image processing that is related to it, especially in MATLAB. So what are we going to be doing? We're going to talk about the ionization. Do you remember what we said about ionization? That the wavelength of these X-ray, the X-rays are high frequencies, which means small wavelength. If you have an atom like this, so this is the nucleus, and then you have orbits, that's simplification of the Bohr's model, and you have, let's say, electrons here, whatever that thing is. If your X-ray is very small wavelength, so it's usually passing through the electrons, but sometimes it's going to be hitting one of the electrons, correct? When it hits that electron is going to be moving away, right? And then this atom is now, because it lost a negative charge, it's becoming a positive. So it's now we are ionizing it. And because it's a positive charge, it means that it would need to interact chemically with other atoms around it, right? That's not good in the human body. That's ionization. So we're going to talk about this a little bit more. Forms of ionization, nature and properties of the ionizing radiation, attenuation, and then dosimetry. Is that correct how I'm saying dosimetry? Dosimetry, yeah. And so dosimetry is a lot about the form of that radiation and the projection, the instrumentation, the image formation, and the noise and scattering. Does that sounds like a good idea? Where we're going to with the thing? And this way you will know, most of the things about the medical imaging for the radiographic imaging. So you've seen a lot of these images. So those are representative X-ray transmission imaging of various parts. So this is the hand, the neck, knee, chest, feet, and pelvis. You can see that it's all about absorption, which is attenuation. So if we are exposing the body with X-ray, those X-rays are going to be absorbed, and usually the thicker the organ, the more absorption, correct? And the more dense the organ, the more absorption. That's why you are seeing bone, right, everywhere in X-ray. Does that make sense? Now, your X-ray image is a representation of the attenuation of the X-ray. You need to keep that in mind. Now look at this. If you have metals in the body, look how bright they are because they're very dense and they're thick. So they're absorbing X-ray, or they're attenuate. We don't say absorb. They attenuate X-ray by a lot. Make sense? So you have surgical fixation device. Do you know what we do with this? This is called fusion, where you have two vertebrae and you screw some plates and screws around it so that they don't move. And this is treatment for people with arthritis, because if you have arthritis, the bone will be moving on top of another bone, and that's very painful. And you have total hip replacement, the pelvis showing artificial hip joints, and see the knee showing bone fixation wires. So those are X-ray. Now this still, that's an X-ray. Now the CT scan is still a radiograph project, a radiographic image projection, correct? Now, but the cool thing about the CT scan is that you are taking images from different angles, correct? So you can look at the CT scan images of the body. This is the wrist, torso, and abdominal. This is how they look like. Complete spine. This is the abdominal, the torso. And this is a complete spine, chest, and ankle. Now, what do you see different from the X-ray here? You have a grayscale now rather than a very bright or dark absorption. And that's because we are now, looking at the tissue absorption in 3 dimensions. So this is giving us a lot of information into the the CT of the CT scan of the human body. Make sense? So radiographic imaging is X-ray and CT scan. One of them is a 2-dimensional projection, and the other one is a 3-dimensional image slice. And we're going to talk a little bit about the instruments that build these things, that make these things. Now, let's talk about physics a little bit. This is the planetary atom, right? A common, that's the model. I don't know what they call it. This is, what is it? Not the Bohr model. This is the probability model. It has a name. Because this is the cloud of the probability of where each electron is. It's not the circles. But anyhow, you know the protons and neutrons and electrons. Do you know something called neutrino? Neutrino? The neutrino is, I think 100 smaller than the electron, and the neutrino is a particle. This is particle physics. It's a subatomic particle. But we know that the information that we care about here is that if your X-ray is hitting one of these electrons, then we have ionization. That's bad. If it's not hitting the electrons, we're fine. We're getting X-rays as we want it to be. Now, the X-rays can, pass between the orbits. They can go through a straight line. They can be, affected in such a way that they will change their direction, correct? And they can hit something and move away. So we're going to learn about all these, incidents that happen for these electrons. Now, this is a table that is showing you some of the elements. We have the element. It is the element table, and then you have the symbols. What is the atomic number? Do you know what the atomic number is? How many electrons do we have on the valence orbit, right? The last orbit. How many electrons do we have? That's the atomic number. And the atomic mass is that no?
I think the atomic number is how many protons it has.
Oh, sorry. That's the valence. That's called the valence, the electron. So you're right. So atomic number is the protons, number of protons, and the mass is the protons plus neutrons, correct? Is that how we do? And then the mass number of some unstable isotopes. See, these unstable isotopes are the ones that we usually get some radiation out of them, electromagnetic radiation. Yeah, sorry, the Z is the atomic number. The valence number is the number of electrons at the last, the furthest orbit of it. We good? Now, these things on the right, we call them radionuclides as well, because they're unstable isotopes. So what do they need to do if they are unstable isotopes? They need to radiate energy, correct? To become stable. That's what we know about them. Okay, let's see if we can solve the 3 questions about testing your knowledge from the sheet that I gave you. Let's give it a minute, for 2 minutes, and see if you can get the answers for these. You're going to upload this to the week 4, in-class activity. Yeah, let me give you a couple of minutes and see if we are all on the same page.
Just the first 3 questions?
The first 3 questions, yes. The ones that you see on the screen, yep. We good so far? Okay. So first one, what is the primary principle behind the X-ray image? B. Yep. It differences in the tissue attenuation of the X-ray. That's the most important thing. Now, what is the purpose of using contrast agents? So if you're adding an agent to the body, what is that going to help us? Yeah, it's going to enhance visibility of soft tissue, correct? Because it's usually going to either enhance or inhibit attenuation in that organ that we're looking at. Now, the last one, what property of tissue determine the amount of X-ray absorption of the tissues? Also B, right? It's the density of the tissue and the atomic number. So we know that if the tissue is denser, you're going to get more attenuation. How about the atomic number? If you have larger number of protons, you also get a larger attenuation actually with it, right? Because it's a bigger nuclei that we deal with. Make sense? We good with that? All right. Questions? No? Cool. All right. So here, now the arrangement of the electrons in the shell, that's for the carbon atom. So we have 6 electrons, and it's stable. And those, you know, those are the orbits, the shells, KLM, and how many electrons we have to have in each one of them, electrons. Now, why is this important? We just want to make sure that ionization, we have an ejected electron, plus the ion have more energy than the original atom, which means, if you remember Gibbs free energy, atoms likes to go to reduce its energy. They don't like to be at higher state of energy, which means there will be these ions will aggressively try to, do chemical reaction with someone else to reduce their energy with some other atoms. And that's the problem if you are, ionizing the DNA. Now the DNA is actually being destroyed with other elements around it, chemical elements. So you have your atom, this is your radiation. Let's say you are knocking this electron free, and then now we have a positive ion. Now the unbounded energy plus the electron energy, they are usually greater than the bounded energy, right, of the radiation, and that's an unstable state. We just want to look about some safety issues about the X-ray. I'm going to come back to it later on as well to talk about it. Because as an engineer, safety is an important aspect to keep in mind. Now let's talk about the frequency, the spectrum of the radiation. See where X-ray are? They're 10 to the power 18 to 10 to the power 20 frequencies, right? Now, if you have a lot of high frequency, it's a very small wavelength. That's why they can go penetrate these atoms. So anything below this is non-ionizing. Anything above it is ionizing. However, the radio frequencies. Now, do you know how the cell phones are in the 1 giga frequency? There's a lot of debate about the cell phone frequencies, that if they are ionizing or non-ionizing in the air, and how long that takes. But just keep in mind that this is where we work with. Your microwave actually instrument is a dangerous instrument if you're close to it. It could somehow ionize objects.
Isn't it bad to look at the microwave while it's on?
Because your eye is very transparent to the retina, and if there is any radiation coming to the retina, that could be damaging your vision. Make sense? We good? Okay. Now ionizing. Are we okay with what the problem with ionization and some concepts behind it? Now, and that's radiographic imaging. Now, form of ionization radiation, we have something called particulate radiation, and we have electromagnetic radiation. So both of them are used to make devices for us. So any subatomic particle, a proton or a neutron or electron, can be considered to be ionizing radiation if it possesses enough kinetic energy, or you can have an electromagnetic radiation compared to an electric wave. You know, an electric wave is just, you know, a sine or cosine in 2D, but if you have a magnetic wave imposed on top of an electric wave, you're getting something like this at the bottom. Now this is what an electromagnetic wave look like, and that's your X-ray. So electric wave and a magnetic wave traveling together with a 90-degree angle, that's radio wave, X-ray, and gamma rays, all the, you know, usual waves that we have in the body. Now we try to stay away from particulate radiation because it's a tricky concept to look at particles only, because particles are actually waves and particles at the same time. So, but that's for another day to talk about it. Now, ionizing radiation. The image you sent, this one below, explains that ionization radiation is a type of radiation that has enough energy to strip electrons from atoms. That's the most important thing, right? And creating ions. There are two: the particulate radiation. Now this is tiny particles, and those are the, you know, this is similar to what we talked before in the previous slide, but I just wanted to make sure that it's stripping electrons from the atom, just to make sure that that is clear, what this ionization mean or radiation mean for us. Cool. Now, we have several applications in biomedical engineering. That's crucial to handle it with caution due to potential for causing harm. So where are those? What is medical imaging? This is clear. X-ray, we create images of the bone. CT scan, combine multiple X-ray images to create a detailed 3D image. Is that correct? Good. Now, PET and SPECT, those are the nuclear. This is positron emitting tomography, right? Positron emission tomography. So you use radioactive traces. Remember the unstable elements that I showed you? You can put them in the body and they will be doing radiation outside. Metabolic activity of the body. Nuclear medicine, radioactive isotopes used to diagnose, and therapeutic purposes for cancer, especially. Now, radiation therapy, that's another thing to kill cancer cells with focused radiation. So it's getting now attracting more and more attention because it can be really, really, you know, have a high specificity if you do that. Now, sterilization is also another application for ionizing radiation. That you sterilize medical equipment by killing microorganisms. And then you can do it in research using study biological processes and cellular level. What we care about is medical imaging. We good? Make sense? But ionization is a very important concept for us to understand if you are designing medical equipment or calibrating medical equipment or selecting medical equipment. Cool. So let's talk about the frequencies and how much energies they have and the wavelength. The smaller the wavelength, the higher the energy, right? And that's the gamma rays. That's mega EVs. It's just to keep that in mind. Now I like to make a comparison between the particulate radiation and the electromagnetic radiation and their applications and the dosages used in medical imaging. Are we good with this slide? The higher the frequency, the higher the energy. And then those are the types of, you know, waves that they're coming out of the whole thing. Alrighty. That's why radio waves are actually used in ships, because they have large wavelength so that they can go along long distances without attenuation. But the larger the frequency, the more dangerous actually, because of ionization. Cool. So let's talk about this, the nature and properties of ionizing radiation. So we have, are we good with particulate and the difference between the two? So what are we going to learn about? We have some imaging characteristics, and then we have dose-related characteristics of the two. And we're going to discuss them just in a little bit more details. So for particulate radiation, if you have electromagnetic radiation produces when charged particles are decelerated by the electric field of the nucleus. So let's say you have a nucleus and you have these electrons, right, around it, and you have an electromagnetic wave, X-ray passing through, right? If that electromagnetic radiation, we can create a radiation from a charged particle are decelerated by the electric field of the nucleus. So if that is moving, the X-ray is moving between the nucleus and the electrons, and it becomes slower, this atom is going to create other radiation on its own. We have something called characteristic radiation, X-ray emitted when an electron transition from a higher energy level to a lower energy level, right? Sometimes you knock off one of these electrons to another level. That's unstable. It wants to go back. As it goes back, it does radiation, right? So we're going to talk about, how can we create an X-ray? These are the ways that you excite something to get the electrons to go to a higher level of energy, and then they need to go back. As they go back, they do radiate, and that's your X-ray. Then you want to look at. Positron annihilation is when you have a positron and electron. I told you we have some radioactive materials that they emit positrons. These positrons, if they are in the body, and one of them is seeing an electron, they annihilate each other, and then we have a gamma ray coming out of it. So when we talk about creating electromagnetic waves, how can you create it? Does it make sense? Which is the source? Remember, when we like to take an image, you need to have a source and expose the body. Now, at the source, what can we do? These are the things. Positron range, the distance positron travels in a material before annihilating itself with an electron. These are important characteristics when you design an ionizing radiation equipment. Now, this is particle. Are we good with particles? This is what electrons are doing and positrons, and it's happening with particles. Now, when we talk about electromagnetic waves, we have something called attenuation, which is the reduction of intensity as it passes through matter, and that's how we detect. So I want you to think about that. We have a source, right, a subject, and a detector, right? So attenuation is an important property. We have something called photoelectric effect, the absorption of photons by an atom, resulting in injection of an electron. So let's say an atom is absorbing energy from a photon. A photon is a wave. If it's absorbed it's unstable now. It releases an electron. That's called photoelectric effect, connecting the photon with the electrons. Are we good with that? And then we have something called Compton scatter, which is the scattering of photons by an electron, resulting in a decrease in the photon's energy. So you have photon moving close by an electron, then the electron is moving, changing the direction of the photon, and that is going to decrease the photon's energy. So these are important aspects into the creation of radiation, especially in imaging. Those are important concepts. And so if you're looking at a medical imaging instrument, you need to compare two instruments. You need to look at these concepts and what are the values between the two. We good? Make sense? Okay, so let's go with the dosages. So here, we have some characteristics about the dose that you can select and you need to identify. We have something called linear energy transfer, which is the amount of energy deposited by radiation per unit distance traveled. So let's say that I have, I don't know how many inches is my body. How much is energy deposited in my body as the X-ray is traveling? That's called the linear energy transfer. Right? That's we measure. And then we have specific ionization, the number of ion pairs produced by radiation per unit distance traveled. Remember, X-ray depends on how large distance traveling in the body. Now we have air kerma, which is the kinetic energy transferred to electrons by ionizing radiation per unit mass of air. Right, so this is very important for dosages. So if you are speaking with a radiologist, they need to know all these numbers from their device. And then the dose is the amount of energy absorbed per unit mass of tissue. You need to reduce this as much as possible as this exposure. And we have something called dose equivalent, which is a measure of the biological effect of radiation, taking into account the type of radiation and its linear energy transfer. Effective dose is a measure of the overall health risk associated with exposure, and the F factor is a factor used to convert absorbed doses to effective dose. So the effective dose is a measure of the overall health risk. That's what we want to make sure that we know, and radiologists always try to track. These terms are important for understanding the interaction of ionizing radiation with matter and its effect on biological systems, and they are used in various calculation and assessment related to safety and application, right? And we're going to talk about safety. Safety is very important now in X-ray. We good? Sense? Okay. So let me move to, okay, let's take a 5 minutes break just to refresh and stretch, and then we'll continue with the energetic electron interactions and see what was going to do. We good? Let's take a 5 minutes break. I know it's sometimes boring, but I don't want to lose you. Okay, we're good to go. Now, are we good with all these characteristics and names and terms in the comparison between particulate and electromagnetic wave radiation ionizing? Yeah. So both of them are used in creating X-rays, and hopefully now we have at least a good knowledge of the terminology used for those. Now let's move on. So here now this is the primary energetic electron interactions. So you have A collide with other electrons until they lose their energy, correct? So electrons, you keep colliding, and then they lose their energy. Make sense? Then B, you have eject a K shell electron. So one of them is just the K shell are remember the shells are the closest to the nuclei. Those are the highest. They have a lot of energy because they are very close to the nuclei. Generating, this is what we call the characteristic X-ray. Are we good, guys, with this? So if you are creating an X-ray machine and you want to generate characteristic X-ray, you need to target the electrons in the closest shell. When we lose the electron, the ejected electron, there is a vacancy in the inside, correct? An electron from an outer shell needs to go in to replace it. When that happens, we have an characteristic X-ray generated. Does it make sense? So a closed, shell electron was removed. Another electron needs to replace it from an outer shell. When that happens, a characteristic X-ray rays are generated. Now, we have bract by a nucleus generating I need to see if I can do this correctly. How would you say this? How would we break it? Say it again.
It's a German word. It's
Yeah.
Bremsstrahlung.
Bremsstrahlung. That. You take German? Okay. So these radiation happens if you have an X-ray, an electron, but it changed speed because of the nucleus. It creates an X-ray, and a special type of radiation. Does that make sense? Yeah, we are building the device now. We are learning how to create this radiation that can be used. Now, we will go. So, what are the energetic? See the characteristic radiation, the X-ray from tungsten. It has the largest relative X-ray intensity, right? The top here, and the Bremsstrahlung is, getting you lower energies. So this is the photon energy in keV, which is kilo electron volts. That's how much energy it has, and that's the radiation intensity. Now, the energy itself of the photons created by that X-ray device or radiation is a function of the energy. So that's important. So when energetic electrons bombard a target, the ones that we are, a specific element, two kinds of X-ray produce, characteristic X-ray and the Bremsstrahlung X-rays. Low energy X-ray of both types are absorbed by the medium, and the low energy are the one here, right? So you need to make sure that you have large energies to get it there. Does it make sense? We good? Remember, you're going to have some electrons. You're going to target an element. That element, something's going to happen to it by knocking some electrons in it itself by the photons that you are seeing, and then that radiation will be created. And I'm going to show you some images. So incident photon getting there. Then we have something photoelectron, as I mentioned before, characteristic radiation. We have Auger electrons happening and moving. So this is the effect of the photoelectric effect when a photon is, been affected by an electron, right? That's a very important also way of generating X-rays. And Compton scattering, as we mentioned before, as I explained that to you. So we're talking about ways of how can you create characteristic radiation. How can we create X-rays, right? That's what we're looking for with it. Okay, so questions. So let's take a couple of minutes and see if you can answer these 3 questions. So 4 to 6. Those are, now we talk about the fundamentals of the imaging. Oh, sorry, 4 is the X-ray system components and physics. That's what we're dealing with. Remember, for X-ray, we try to do the X-ray generation in a tube with vacuum, and you have an anode and a cathode, so that electrodes moving to the anode, correct? To be able to be changing. And I'm going to show you that image in a bit. But let's see. So this is just getting us to the next step with imaging. Okay, you want to try it together? Okay, so for the first one, in an X-ray tube, so usually if you have a tube like this, you will have an anode and a cathode, and there's something need to be bombarding a material so that you generate the X-ray from it. So in an X-ray tube, what is the function of the anode? And the anode is to stop electrons and generate X-ray. So the cathode, so this is cathode, oh sorry, no, the other way around. So let's say we have this tube, right? This is the cathode, right? And that's the anode here. That's the anode. So the function of the anode is that you are creating electrons going here, stopping the electrons, and then generating X-ray. Does that make sense? And then you will be selecting the type of the cathode material and the anode material in such a way that you maximize your output of X-ray. Right.
So the cathode produces the energy?
Photons or electrons, both either ways. That's going to be affecting the material of the anode to create, to remove their electrons from their place and then create an X-ray. Yep, you're right. Does it make sense? And that is C, right? That's the anode. The anode. Now, which of the following factors affect X-ray image contrast the most? Contrast, which means absorption, correct? And if you look at the contrast, remember that curve that I showed you? It depends on the keV, the kilo electron volt. So that's the kVp, which is kilo electron volt peak. So that's the X-ray tube voltage. The larger the X-ray tube voltage, the larger the amount of electrons, and then the more contrast that you have in your image. Right? If you have low voltage, low contrast. High voltage, high contrast in your image. That's why when we buy X-ray machines, they will talk to you about this kVp, the kilovolt peak for it. And the larger the value, this value, the more expensive the device is. We good? Make sense? Now, what is the main advantage of using digital radiology over conventional film-based radiology? So it's lower radiation exposure and faster image processing. It's the most important thing is faster image processing because it's digital now, right? And you know that's the main objective of something like that. Make sense? We good? Questions? All right, next. Let's talk about some of the processing because we started talking about processing before. Let's take a couple of minutes and see if you can get these answered from 7 to 9. And some of these things, you know, Sobel and Laplace, you're going to see it in the lab when we create these filters. They're similar to the kernel that we created. Remember the 3x3 and the 5x5 matrices? It's the similar thing. Computed radiology is computed tomography, just as CT. So I would like to just present to you some of the important terminologies and concepts related to ionizing radiation or radiographic, imaging. You good? Okay, so the first one, what image processing technique is used to enhance edges in X-ray imaging? It's edge detection, right? It's the same thing. And remember, for X-ray, you have only mainly two levels of grade. One that bone and the other non-bone. That's what you're looking for, right? Unless you're doing a CT scan, and that's more processing for you. So it's edge detection. Now the Sobel and Laplacian edge detection techniques, we're going to learn about them in the lab, and they're just to show you the edges. Make sure that they're between different tissues. Okay, which of the following is a common post? So this is C right here. Yeah, just make sure that's C. Now, which of the following is a common post-processing technique to improve X-ray image contrast? Now, contrast, the Fourier transform is just showing you the frequencies, correct? It does not do anything to the image itself. Logarithmic scaling is just multiplying value with values. It's not going to do anything. But noise addition is going to make this worse, correct? So the reasonable one is windowing and leveling. And what we mean by that is that you select which frequency to keep and which frequency to remove. Remember when we talked about high-pass filters? If you have make high frequencies, only high frequencies, you will see the contouring that between two different things. And that's a good common to improve X-ray image contrast process. So that's windowing. I'm selecting a specific frequency, and leveling, I'm making sure that inside that window or whatever the things are in the same values. Remember we did last time low pass filter and high pass filter, and then we had also a booster. Remember the booster? That is give you the contours but also give you some details. That's the leveling. That's the booster. So the window will give you high frequencies, but the booster will keep some details inside. Okay, in a computed tomograph, which is a CT scan, which material is commonly used in the imaging plate to capture X-ray photons? So if we would like to capture photons, I don't know if we know the chemistry about it, but it's the phosphor. The phosphor is the thing that captures a lot of energy because we need to collect energy. That's phosphorus. That's what. You know, with ATP, adenine triphosphate, and adenine diphosphate, and the energy molecules in the body, there's a lot of energy going on with the phosphorus. So phosphor is very important in our body, and deficiency is a problem. But it's good in, absorbing, capturing the X-ray photons. We good? Make sense? Okay, let's test safety. We're talking about terminology here. It's important to keep that in mind. So let's talk about a little bit safety before we move on into the device itself, the structure of the device. So let's take a couple of minutes to see if you can get the answers for these safety and dosimetry, which is the dosages of X-rays that you need to have that. Okay, let's go with this. So let's the first one is which unit is used to measure radiation dose absorbed by the human body? Do you know which one is this? What's that? Anyone knows? It's the gray. GY. So when you look, that's to measure the dose absorption, and that's why if you go to do research in a university and you're working with, let's say, radioactive isotopes, they give you a ring, right, that detects how much radiation is absorbed, and they will report it in that, the gray. Now, what is the purpose of using lead aprons? Is that correct? Aprons in the X-ray? Yeah, aprons. Aprons. I think that you were right with this. Yeah. So, what is it for? We protect against scattered radiation. That's the most important thing, especially for people who work all day with this. Now, which factor helped reduce radiation dose to the patient during an X-ray emission? Remember, larger KeV is better for resolution and also reduces the exposure. So using higher KVP and lower current, that reduces your radiation dose. And I'm going to show you how that affects that. But so it's B. It's using higher KVP and lower MA. Yeah, that's correct. Yes. So if you look, remember the anode that we talked about? Are we good with the questions? Safety? Okay. Now, see, this is your X-ray source, right? So you have your anode. This is the anode, the positive, where you have a material here, but you have the cathode where you are emitting stream of electrons to it. Once we have it in an angle so that we can identify the direction so that it does not scatter everywhere or going back. So you can have these electrons hitting this tungsten target, and then that's your X-ray. Now remember when I told you that lower the current, you need to lower this current here. Lowering the current, make sure that your X-ray are just enough dose. If you have high current, means high electron, very dense X-ray. Does it make sense? How are we looking into that? And this is it should be in a vacuum tube. So this is your heated tungsten filament. Those are electrons going to a tungsten target, and the tungsten is used specifically because it's creating the type of X-ray images that we want from it to be done. And then you have the copper anode, and then you have that thing. So this is electric current is passed through a filament, leading to emission of electrons, then striking a target, leading to X-ray emission. This is what is inside the device of the X-ray device to create that thing. Now there is one thing also. We can have also around it a shield of lead with only some openings to specify in which direction the X-ray images are going, and that we want them to be straight. So you can have something like this, right? With just this opening, allowing the X-ray to go only in one direction. And there need to be parallel. That also increase your the performance of your X-ray image. Does it make sense? Now remember when I told you KeV, the voltage between these cathode and anode, the higher that thing is, the better quality of your X-ray that you're looking for, which means that the resolution will be better. Your contrast will be better. But you don't want to have a lot of current because that's going to create a lot of X-rays. And they could be unstable. Make sense? So we're getting a little bit closer and closer to the devices and the systems of these medical imaging modalities. And we're going to learn more about all of that. So hopefully this lecture was good in terminologies. We know what we're dealing with. And if you're talking to someone, at least we know what they are meaning, what the meaning is for that medical device. Any questions? We good? Make sense? Yeah. Were the multiple choice questions helpful to keep something like this going? Good.
Do you want this turned in, or do you want
Yes.
to hold on?
Yeah, I'm going to make sure that we have
Are we
the.
doing anything with the bat, like the last discussion?
Yes, we're going to come back to it later on, at the end of the lecture. Not at the end of the lecture, in between the slides, there's something about. So let me